Hi, my name is Chris, a postdoc and associate member of ML4Q, and you're listening to ML4Q&A, a show where members from the Matter and Light for Quantum Computing cluster answer questions about their work in the cluster, their research, and the future of quantum. In today's episode, I'm talking to Erwann Bocquillon, ML4Q professor at the Second Institute of Physics at University of Cologne, who started his group in October 2021. We talk about Erwann's educational and research journey, touching upon differences between studying physics in France and Germany. We also discuss electron quantum optics and learn about Erwann's best memory from his PhD time. It is my pleasure to welcome Erwann Bocquillon to the ML4Q&A podcast. Hello, Erwann.
Hello, Chris.
And of course, this is quite exciting. You're a pretty new professor in Cologne, and we actually previous podcast guests have been in other locations, but our offices are within quick walking distance from each other, and we have already talked and even thought to collaborate a bit. So this is quite exciting for me. I wanted to start off by talking about electrons because, in a way, a lot of your research revolves around understanding electrons in the solid state, right? And especially your PhD even quite fundamentally was about measuring the properties of single electrons, right?
Yes, so I think everyone is now familiar with the picture of wave-particle duality in quantum mechanics. So each electron has a dual wave or particle nature, and I think depending on what you look at in condensed matter, you see one or the other, or sometimes even both when you really probe quantum mechanics in the deepest manner. And depending on what you look at, then you can see very different things. Like, for example, if you start constructing condensed matter by bringing one atom close to another, and so on, then you have to put all of the wave functions of these atoms together, and that gives rise to the construction of the so-called band structure, which tells you whether your material is going to be an insulator or a conductor. And that is very deeply connected to the wave nature of the electrons that will evolve in the potential created by the core of the atoms constituting the lattice. So that's very, very wave-oriented picture. But then, once you know whether your system should be insulating or conducting, then you want to predict how well it can conduct electricity. And that is then very, very deeply related to whether the electron will scatter against other electrons, against vibrations of the lattice, against all the impurities in the lattice and things like that. And there you go into a collision picture, which is much more a particle picture, where you really see that you have your electrons seen as beads that will collide, and whether they make it from one contact on one end of your conductor to the other end depends on how many collisions they will undergo. And that is again going from from the wave picture at the beginning to now a collision picture, which is more particle oriented. And I think what is very exciting in the last maybe 20 or 30 years is that there are now materials where the material quality is so good that this collision picture is less and less relevant, because the material is getting better and better with less and less impurities, and you can cool it down to remove the vibrations and so on, so that in a way you recover this wave picture in the transport properties of your material. So you can really explore the wave properties or the quantum properties of transport in these so-called quantum conductors at a very fundamental level, and this is something which I find extremely fascinating.
Yeah, me too. I think somehow when we scientists we start thinking about experiments, we always have to have a picture in our head, And indeed, part of this picture can be this Bloch picture of that you have a lattice of the atoms and that you have the waves, or that you have sort of electrons that scatter together like in a particle picture, which is almost that where you think in a way like in terms of almost Feynman diagram like things, right? But we have, like, when we do our experiments, of course, there's a lot of math. Like, in the end, we have a simple picture in our mind, but in the end, there's a lot of math that we need to do, and these pictures will give you some results, right? But having this concrete picture in your head is still important for coming up with what to do, with coming up for a story for how to sell your results, and so on. So I always find, so when you think of an electron, what is the image in your mind that you have?
So I think, again, in those clean materials, there are very often ways to picture your electron as a wave that propagates in your material, and where you can really start to make the typical things that you do with waves, such as in optics with light, or such as surface waves on the surface of water. You can make them interfere. You can make interference experiments, such as in optics, and there the wave picture is fundamental. Now, of course, we always keep in mind that our electrons have a particle nature, which means they are granular in a way, and each of these electrons carries one charge, and that can also give rise to another type of picture where we, for example, probe this granularity and try to, for example, realize single electron source. What is a single electron source? It's something that from a particle side only carries one electron, meaning one charge, but still has a wave aspect, which means you can make interferences of single electrons. And then comes the question, where's the boundary between wave and particle? How do they meet? How do you reconcile the two pictures? And that's where quantum mechanics is fundamentally involved.
Yeah, I think with this wave picture, I mean, the most fundamental thing, of course, is that in the wave picture, you can have two waves that interfere together. And if you would assume that it's just, if you had particles and you put particles together, you get more particles. But for the waves, it will, in a way, give you positions where you will never find the electron, or like you can have two electrons that at certain points will never will never together go in a certain way, or you basically have this interference aspect where two things can actually give you less when you add them up or more, while in the particle picture you would never get that, right? That's sort of the important part. I mean, in my head, an electron, I always think of them as maybe a little ball that maybe has a little clock, and when it meets another ball, they check their clocks against each other, and that's how they interfere. I don't know if you have like pictures like that in your mind sometimes.
Yeah, that's actually an interesting picture to marry both wave and particle nature. There's also something which is to me very interesting, is something that comes when you do not consider only one electron but many. So let me try to explain. So if you do interference from a wave picture, you only need one electron or one photon. You need one wave that you're gonna split in a, let's say, a double slit experiment, for example, in a Young slit experiment, and you will recombine these waves and you will see the interference pattern. But this is in a way a single photon picture or single particle picture. You don't need to involve several electrons or several particles to see this. But quantum mechanics also predicts that when you put many particles together, they must have some kind of collective behavior. For example, bosons, they like each other. The hand-waving argument is that they like each other. They tend to bunch. These are they have this tendency to always group together, while fermions, in a way, do not like each other. They can't occupy the same state, which means if you try to put two electrons too close to each other, regardless of the Coulomb interaction, but just by nature of the quantum mechanics, they will not like that, and they will not allow for this. And this means that very deeply in your experiments, you can probe these so-called quantum statistics, and you can see whether the particles you manipulate are bosons, such as photons, or fermions, such as electrons. And that has very strong consequences in the electronics, that in the experiments that we realize. And I think this is also a very interesting aspect. And I think we might cover this a little bit later.
Yeah, exactly.
Beyond bosons and fermions, there's another type of particles which are anyons, which are even weirder and show even weirder collective behavior.
When did you start thinking about these things? Did you already get interested in physics early on in your life, or was it more that you gradually got more interested in these aspects?
I think very early on I became interested in science in a broad sense. I was reading books for kids about science and technology and things like that very early on. And I always had this attraction for science. But there are a few very important steps in my life that pushed me gradually more and more towards a career in research. One of them was an internship which I did at the very end of my junior high school, where I went to a particle accelerator and where I spent 1 week observing the different people, the different type of work that could be done there, from science administration to the technical aspect of fixing the infrastructure, the engineering aspect of designing new detectors and things like that. And that really pushed me deeper and that really drove my interest for science. So after that, I decided that in high school and afterwards, I wanted to study physics, and progressively continued step by step towards research in an academic infrastructure.
Yeah, I mean, now, of course, you and we both do work related to electronics. And I was thinking, like, also for me, I wasn't that aware as a child or a young adult. I wasn't actually thinking that much about electronics yet, because the first way that we get into science is maybe reading books by Stephen Hawking or something, which is a lot more in the clouds, right? Than to think about electronics and so on.
So from my side, what I can say is that I've never been too much into astrophysics. I've always been more interested in the technological aspects also. But I must say I wanted to do optics until very, very late in my studies. At the master level, I was still mostly focusing on optics lecture. I did an internship on optics in Canada at the Institute for Quantum Computing. And I really considered that this was, for me, the best path. And then at the PhD level, I needed to find a PhD, and I ended up doing something which was completely different, doing condensed matter, electron transport, but there was still a bit of optics in it because the title was Electron Quantum Optics. Yeah,
exactly. That's it's just a remarkable thing. I mean, to me, it always, like, I mean, in our youth, let's say the early 90s and so on, we started to have Game Boys and electronics and so on, and certainly all the understanding of electrons in metals and semiconductors has been the driver of a technology that we, I guess, as a generation really grew up with more than other people. I mean, other people had, like, let's say, the telephone, but we had Game Boys in our hands. There was the first cell phones and so on. And so we grew up around all this electronics marvels. But I also feel that I didn't appreciate it as much. Like, I would say that for me also only during the university studies did I understand how deep quantum mechanics was related to all of this. Like, this link between understanding how electrons behave in materials and how our society is being sort of really changed by technology, this link wasn't as clear to me to begin with.
Yeah, I can fully relate to that. As I said, I was interested in both science and technology, so I always had an interest for technological aspects, but I never realized how much of the science was involved into the technological aspect. This came later, and that's something I really enjoy now, this ability to be at the interface between fundamental science and maybe potential applications for the industry. I mean, we are still very, very oriented towards fundamental research, but I like to keep an open eye for opportunities in this direction. Also, I always remember something that one of the professors at the École Normale Supérieure, where I did my studies, said. This was Jean-Michel Raymond. He once said in a conference that nowadays something like 70% of the industry is heavily connected to quantum mechanics. And that can go through lasers, through semiconductor industries and things like that. And I think this is a number that shows how important quantum mechanics has become over the years.
Yeah. I mean, maybe exactly. Let's follow a bit your career path. And I of course I read a bit into your CV. And what's fascinating as a German person is to read the beginning all the way. I mean, eventually there's just a master in quantum physics, and that of course we all understand. But on the steps there, you have the classe préparatoire and then the École Normale Supérieure. And can you explain a little bit what is this path to study in France?
Yes, I can try to explain, even though it's usually not so easy for people outside of France to understand that. At the end of high school, one has to decide where to do studies in higher education. And in France, there are two different paths. There are more, but if you want to do in like a career in research, there are typically two paths you can consider. One is going to the university from day one and start a bachelor in science and then continue with a master and so on. And that's very comparable to what you can do in Germany or in many other countries. The specificity of France comes with the possibility to do so-called classes préparatoires, which are originally 2 years of intense training for taking competitive exams at the national scale to enter engineering schools. These engineering schools are very old. They date back to, I don't know, maybe 200 years ago. Some are, for example, still have a name related to the fact that they were connected to the mine industry. And that's a very, very intense way to learn. You have to consider that you do basically a Bachelor of Math and a Bachelor of Science and a Bachelor of Physics in parallel, plus some literature and philosophy, some English and so on. So you have a very, very heavy agenda. It's very intense. And that's what I chose to do. And at the end of these 2 years, you can take these national exams and try to enter engineering schools. But also there's one exception. One of the schools you can enter is the École Normale Supérieure, which is not really a university, but a place which is still very, very focused towards fundamental research. Originally, École Normale Supérieure there were a few schools that were whose aim was to train future teachers for higher education. So typically, people who would go to École Normale Supérieure would have to take the exam to become university teachers or high school teachers. This has gradually disappeared, and this is more and more oriented towards research. But that's where this schools originate.
So your path was to take the class préparatoire. Then you took the test, and I guess you succeeded because you got a place at ENS.
So I did not succeed in the first place. So I took this second year a second time, and there I succeeded in the second try.
And it's, I guess, it must be very competitive. You have basically everybody from France who took this path taking these exams, and then the École Normale Supérieure admits a fraction of those people, I guess.
Yeah, so there were typically, if you include math and physics, maybe 60 positions at École Normale Supérieure in Paris, about 3,000 candidates. But again, because it's so oriented towards research, the type of written exams that you take for the École Normale Supérieure are slightly different from the standard ones that you would take for other engineering schools. So it also attracts different candidates, I would say. But yes, it's very competitive, and I'm very proud I achieved that.
Yeah, it's really, but it is an amazing place. I guess when you, I mean, it makes sense to me that you would be interested in optics because you already mentioned Jean-Michel Raymond, and I guess he worked with Serge Haroche, right?
Yes.
Which is sort of people who, I mean, Serge Haroche got the Nobel Prize. Jean-Michel Raymond at least was very connected to the work that got the Nobel Prize. So, I mean, those people really got a Nobel Prize. The Nobel Prize was for understanding light at the quantum level for single instances of photons and so on. So it's really a deep understanding of the quantum nature of light.
Yes, so the physics department of the École Normale Supérieure has a very long history with quantum mechanics. There's been a few Nobel Prizes on cold atoms also, like Claude Cohen-Tanouji. Cold atoms is one very strong specialty. These experiments of coupling light and matter at the most elementary level by Haroche and Raymond. There are other aspects which are explored at the École Normale Supérieure, and it's a very interesting place for learning physics.
Did you have lectures also by Claude Cohen-Tanouji?
No, he was already retired at the time where I started, or close to that. But I had lectures by Serge Haroche, by Jean-Michel Raymond, or Jean Dalibard.
Yeah, exactly. Because Cohen-Tanouji wrote one of the major textbooks on quantum mechanics. I really recommend. I think it's a really good textbook, I think.
Yes, so I learned quantum mechanics with this book. I must say I had a friend who hated it because he thought that was not a physics book, it was a math book. It's very, very math-oriented, it's very formal. I enjoyed it very much because of, I think, my background in mathematics was good enough so that I could take advantage of this very formal presentation. But it's also true that the physics is a little bit hidden behind the math. But it's a very good book.
Yeah, I think, but that's also an interesting difference between the French and the German system. I have the feeling, like, from the French people that I've met in research, a lot of them have a really, really good grasp of linear algebra, of theory of functions, of complex analysis. That is maybe better than the average German student.
Yes, I think I agree to that. I think many of the students that end up doing a PhD in France many of them have been through class préparatoire, so have done this curriculum involving math and physics and sometimes chemistry also. So they have a deep background in mathematics. The way of teaching is a bit more formal. It also has its drawbacks. It means that when you start doing your PhD in experimental physics, you've done very little you have very little lab experience, and it can be a little bit scary to enter a lab where you have all of these instruments you've never seen. While my impression is that the German system favors learning by taking part in research groups as a bachelor or as a master student. And the PhD students that I've seen in Germany usually have a lot more experience with lab practices when they start their PhD already.
Yeah, I think actually this is one of the things I think this is one of the reasons I like our job so much, is because the cool thing is that on the one hand, we talked about this idea of having a picture in your head of what is happening at a fundamental level. Of, you say, okay, I have some electrons and they do something, and I have sort of a comic book picture in my head of what happens at every instance. Of course, eventually you need to take a book like the Cohen-Tanouchi or some quantum optics book or something to convert this comic book picture view of reality into actual predictions of what will happen. So at that point, for that, you do need the hardcore math. But then in order to measure it, you do need to push buttons and...
Yes, that's what I find extremely exciting about our work, is that our daily work consists of many different things. You can do plumbing. If you do cryogenic experiments, you always have to put some vacuum pumps and tubes together and things like that. You can do some basic electronics to fabricate an amplification setup. You have to do some coding and programming for interfacing the instruments. You have to, of course, at some point your experiment is hopefully running, so you have to think about the physics that's happening in your material. You have to fabricate the samples in a clean room. That involves chemistry and things like that. And at the end, of course, you have to give some interpretations. You have to work on the theory a little bit. So that's what I find extremely fascinating. And that's also one of the reasons why I chose experiments over theory, because I had the naive impression that theorists were just sitting at the desk the whole day and staring at their computer screen. And I can imagine this is a little bit naive, but that's the picture that I had when I started my PhD somehow.
Yeah, I think I have the same, and I also just enjoy, sometimes when you have thought about things, or when you had, I don't know, a lot of annoying parts of your jobs, like correcting homeworks or something, you can go to the lab and you can, exactly like connect or disconnect the pump, and you do some menial labor, and it's actually kind of liberating sometimes.
Yes, hands-on physics. You really do things in a practical manner, and you have to connect many decades of experience in many fields to make this experiment happen, and this is indeed exciting, sometimes liberating after grading exams. Yes, I like that very much.
Yeah, I think so. You started a PhD in the group of Gwendal Febb on electron quantum optics. And I think we have to mention another aspect of the French system, which is that, I guess especially at places like École Normale Supérieure, you have relatively small research groups with relatively few PhD students, right? So you joined the group of Gwendal. How many PhD students were there at the time?
Yes, so the French system, I think, is often made of teams of several permanent researchers working on similar aspects, on similar experiments, or sometimes even on one unique experiment. We have mentioned the group of Arroche. There were at least 3 permanents that I can name right now: Serge Arroche, Jean-Michel Raymond, and Michel Brune. And then came later some younger people, and they were all working together on a single experiment. So this means that you have several permanent researchers of very high level that work on 1 or 2 experiments, and that will typically supervise a small number of PhD students. So the supervision ratio is usually very, very high compared to Germany.
Yeah, close to 1-to-1.
Close to 1-to-1. I think there's a rule of thumb that says that each supervisor can have at most 3 PhD students.
Yeah.
And that I found very good as a PhD student, because I had daily supervision with Gwendal, and Gwendal is a great scientist. He's also a great person. And I think we had very good connection. We worked very well together. So I really enjoyed that time. that also has its limitations. First, if you want to tackle a large-scale problem, you have sometimes a hard time reaching a critical mass where you would have several PhD students working on different aspects of a similar problem and reaching this critical mass to tackle a complicated problem. Typically, if you start working on a new material, you would like to have 3 or 4 students, each of them tackling a different aspect. And that can be a bit difficult sometimes. One other limitation is maybe also the fact that because so much money goes into the salary, there's maybe less money for equipment and for general large-scale funding. So that created a little bit of frustration for me at some point when I was in Paris. It has these disadvantages and drawbacks.
Yeah, but indeed, and just to be clear, I mean, Gwendal was still working in the lab with you.
Yes, so Gwendal was about, I think, 37 or 35 at that time. He was a starting assistant professor or associate professor. And I remember that he would typically show up late in the afternoon and ask what I had done during the day, and then we would start chatting and continuing the measurements, and for like maybe 2 hours he would be starting measurements on the computer while I was fixing cables directly on the fridge, and we would interact very, very deeply, very, very regularly, and that I enjoyed very much.
Yeah, and I think it's fair to say, like, in Germany, that is already would be quite unusual. Like the amount of time even early career professors can have in the lab in Germany is pretty limited.
Yes, I do feel that now that I'm in Germany. Now, to some extent, this is also becoming worse in France. I think the administrative loads are increasing with the multiplication of grants and grant applications and things like that. So Gwendal himself right now has very little time to be in the lab. And I think Gwendal was maybe exceptional in that sense when I did my PhD.
Yeah. No, so exactly. Let's talk about your PhD. We're talking about electron quantum optics. When you started your PhD, how much of the PhD path was laid out and how much was unclear?
So the project was very clear. I think so we wanted to do this experiments inspired by quantum optics, but now with electrons, based on this idea that I mentioned earlier, that the electrons behave as very clean waves in high quality materials. So you can start to do quantum optics experiment with these electrons. And there was a very long history in the group of working on this system. So there was a very, very clear path for me, and the direction was very clear. Now, that being said, it's never clear how far you can go, how fast you will move. And I remember someone joking about the fact that my PhD project was actually exactly the same as the PhD project of the student who had started 15 years ago. Because the project the progress had been so slow that it had taken 15 years to get there. And that doesn't mean that the experiment was unsuccessful. There's been lots of very, very nice papers in the years before me. But it's just to show that the topic was extremely rich and there were many interesting phenomena to see on the way. And I think there was a clear path, but you can always be attracted by different directions here and there at different moments, and we did things that were not directly in the line of research initially thought.
So the material system was gallium arsenide, right? Or
Yes.
which is gallium arsenide in combination with aluminum gallium arsenide.
Yes. So gallium arsenide, aluminum gallium arsenide are so-called heterostructures, which means you stack different layers of gallium arsenide with different concentration of aluminum. And you do it in such a way that you can trap the electrons in a given plane at a given interface between two different layers. And that gives rise to the so-called two-dimensional electron gases, which are two-dimensional systems, as their name indicates. And these two-dimensional electron gases show extremely high mobility and extremely high quality of transport. And that comes from the fact that gallium arsenide and related materials are extremely well controlled now and can be grown with high purity. So that in the end you have maybe one of the cleanest system to study electron transport. And I think gallium arsenide has been one of the wonder material in the field for the last 40 years.
Yeah, exactly. Interestingly, it has sort of, early on in transistor days, it was a good system to do things with, but it sort of lost out to silicon and silicon MOS technology as a technology platform, and is only used for like really specialized applications, I guess.
Yes.
So
like high electron mobility transistors can be based on gallium arsenide.
Exactly. So the amplifiers, essentially some of the best amplifiers that you can build are based on gallium arsenide. Maybe some high power applications can be useful, but yeah, other than that, it's sort of never been the thing that you build a computer out of, but it has been a much better platform for fundamental research.
Exactly.
And sort of what are the so the goal of your PhD was to essentially interfere single electrons on a beam splitter?
Yes. So we mentioned earlier the fact that one can do interference experiments with typically one electron or one wave function that one splits and recombines. And this is called single particle interference because it only involves one wave function. But quantum mechanics, as I mentioned, also is gives different predictions when you take several excitations, like several electrons, based on the fact that they are fermions. And you can do so-called two-particle interferences by sending two wave packets on one against the other. So you now have collisions between two electrons coming from two different sources. And if these electrons are identical in the sense that they have the same wave function, then then quantum mechanics or quantum statistics predict that these electrons should avoid each other due to Pauli's exclusion principle, and that collision between these two electrons will then leave a footprint of these quantum statistics in the fluctuations of the current that you measure. So you have to imagine now that we have used two single electron sources. Each source generates a single electron, and we try to match the wave functions of these electrons. So we try to make the sources as identical as possible so that the wave functions are merely indistinguishable. And this means that when the electrons will collide, then they will undergo this Pauli exclusion principle, and then they will have this fermionic anti-bunching behavior. And by measuring the current fluctuations at the output of the circuit, then we will be able to see the footprint of these quantum statistics.
And how many of the building blocks for this experiment were ready to go?
So the PhD thesis of Gwen Dalfev, my advisor, was about building the single electron source. And that was a few years before me, approximately 5 years before I started. And so when I started, the single electron sources were available, and then we had to work into getting the right sample with the right devices that would be fully functional with all single electron sources working and being sufficiently similar so that we could generate this collision experiment. We had to work on the current fluctuation measurement setup. But yes, the building blocks already existed to some extent.
Cool. Then you have another really important thing. The beam splitter in this experiment is actually a quantum point contact, isn't it?
Yes, it is.
And so a quantum point contact, in a way, is possibly, this is something from like basically 1989, 1990-ish.
Yes, late 80s, early 90s.
Late 80s, early 90s. And it was also discovered, I suppose, on gallium arsenide.
Yes.
So what you do is you have this two-dimensional electron gas and gallium arsenide, and you used basically two electrodes to create a very small constriction, right?
Yes. So you create a very narrow constrictions, and you only a certain number of wave functions to go through, because you now have to imagine that you're basically creating a very 1D channel inside your 2D electron gas, and only the wave functions that are matching this very narrow constriction will be allowed to go through. And that's a way of selecting how many electrons, how many electronic wave functions you want to see crossing your interface. Now, if you close it even further, then even the wave functions that are small enough will not necessarily make it to the other side. By that, I mean that there's a finite probability that an electron can be transmitted, or that the electron can be reflected. And that's exactly what the beam splitter does in optics. It reflects photons with a 50% probability and transmits photons with 50% probability. Here, the quantum point contact can be tuned to give any probability of reflection or transmission. So this is even more tunable, but the idea is the same. You create an interface which is only partially transparent for the electronic wave functions.
So as an experimentalist, if you want to just tune your beam splitter, you can just measure currents, and you can play with voltages, and you can get to a situation that you get 50-50 transmission.
Exactly. You know how much current you inject, and you know how much current goes through, so that gives you the transmission probability, and you can tune it.
So how do you make let's now talk about, like, we have this beam splitter. Let's now talk about how to create single electrons that you can put to this beam splitter, and why it is hard to make them identical.
So the main idea behind the single electron source is the fact that you need to be able to isolate a few electrons in a system, in a condensed matter system that contains billions and billions of electrons. And to do that, you use quantum confinement, which means that you will create a very, very small region in space, which is called the quantum dot, where the electronic wave functions are so confined that only a few wave functions are allowed, the ones that match the dimensions of the device. And that means that you will create in this confined region regions with only very few electrons, and they will occupy very specific energy levels. And in that sense, it exactly resembles an artificial atom. In an atom, the electrons are trapped in a very confined region in space, which is the potential, the region which is created by the attractive potential of the nucleus. And these electronic wave functions then occupy discrete levels. This is one of the early results of quantum mechanics. And there we exactly do the same. We confine the electrons in a very narrow region and force them to occupy very specific levels. So now we have isolated a small number of electrons next to our system, which contains many of them. And now what we want to do is push them one by one into the system. And by that, we again use electrostatics. So we change the potential locally. And what you can really imagine with a hand waving picture would be that you really push in and out electrons every time you apply a voltage pulse on your artificial atom. And by doing so, you can synchronize the emission of an electron into the system with the application of the pulse onto this quantum dot.
So as a PhD student, you needed to, on the one hand, make these structures, which are nanostructures?
So the nanostructures were always fabricated by our collaborators in Marcoussis.
So you have these gate structures on the gallium arsenide chip, and then you basically have to, on the one hand, tune the beam splitter to the right conditions, and you have to tune these electron sources to the right precision.
Yes.
And you have to make them push out exactly these single electrons.
Yes, so that involves synchronizing the emission pulses. That involves fine-tuning the emission condition. Of course, if you push too hard on your quantum dot, then you can emit 2 electrons. If you don't push hard enough, then you will emit 0. So you need to find the right pulse sequence and the right pulse amplitude to exactly emit one electron with each source. You can also tune some extra parameters like the coupling between the quantum dot and the 2D electron gas to play a little bit on the shape of the wave function with there are only a limited number of parameters you can play with. So you don't have the full tunability, but we could arrange it in such a way that our wave functions were relatively similar and we could see this correlation, these specific features in the current correlation.
So, and I guess these correlation measurements, that's, some computer programming and some, because in the end, the currents that you measure are tiny. The currents that you measure are carried by single electrons at a time.
Yes.
And you need to measure this current without losing, you need to not lose your sort of small currents.
Yes. So to give you an order of magnitude, if you drive 1 electron every nanosecond, that's about 0.16 nanoampere. So that's rather small. So of course, if you drive electrons much more frequently, then you increase the current. But there are limitations to what you can do technically. So we were typically driving 1 electron every nanosecond. And yes, indeed, that's a very small current. And on top of that, you only want to measure the correlations or the fluctuations of these currents. So that
your noise needs to be much better than this.
Yes. So you need to be extremely accurate and you need to average over very, very long times and many, many repetitions to be able to see clearly these features in the current fluctuations.
Which means not only do you need to tune your setup to match all the right conditions, but after tuning it needs to be stable for a few hours to be able
more than a few hours. When I did my PhD, that's actually a very nice memory that I have of that time. We had a rather elementary way of doing the amplification and the current fluctuation measurement. This has improved massively over time, but at that time we were able to measure about 1 measurement point every 10 hours. And basically we knew that we had a window of about 2 months to measure the data for this experiment. So for 2 months, Gwendal and I would do shifts where I would come very early in the morning and leave around 2 or 3, and he would come at noon typically and stay around 2 or 3 until 2 or 3 in the morning. And we will have this shift for like 2 months to be able to collect enough data for a paper.
So exactly, in the end, the point is that when your 2 electrons arrive at this beam splitter, they go their separate ways and they don't go both to the left or both to the right.
Exactly.
So in principle, if you could measure the experiment perfectly, let's say you could detect every single electron that you get, you could essentially detect this with like, let's say 10 or 20.
Yes, and that's where optics is fundamentally
different, because in optics they can detect a single photon. So when they want to do this type of experiment, in principle, I mean, in optics, the two photons either go both to the left or both to the right. So the optics people can do this experiment in, let's say, the blink of an eye.
Yeah, so they can, the tools are very different. In optics, you can detect a single photon with very high efficiency, but your detector has a dead time, so you can't repeat the process too rapidly. So you need to collect some statistics, so you need to repeat the experiment, but you can only do it at relatively moderate rates. Yeah. In electronics, that's very different. You can do this relatively fast, but with a very bad efficiency. So we still need to average and collect statistics, but in a different way. So we use slightly different point of views. We use slightly different description, and we measure something which is called the power spectral density, which is a measurement of the current fluctuations. In the end, it's all the same, but it's just driven by the very different properties of the electron versus photon detectors.
Yeah. So there's a lot of math in between what you measure and what the optics people measure. Like there's a little bit of math to do.
There's a little bit of math,
say, but in the end, and I mean, you guys got a spectacular science paper out of this. Do you know how many electrons you had to average to get the result?
So I said
about
2
months with nanosecond precision. Right?
2 months with 2 months with a nanosecond repetition rate, so you can calculate how much.
It's an enormous amount of electrons for sure. But I mean, okay, so at that point, I mean, so I guess you guys, while you were doing this experiment, you were also aware that it would be a spectacular result. So that's a good motivation to work in basically complete shifts for 2 months.
Yes, that was a long-awaited results, both in our groups, but more generally by people in the community. We were extremely motivated, and it's true that it helps. I think we were also fundamentally driven by our interest for fundamental science, and we knew it was a very spectacular results to be sold, but it's also a very strong and simple manifestation of quantum statistics and quantum mechanics. You create a huge apparatus of dilution fridge, many instruments, and so on, and in the end you verify at the simplest elementary scale of single electrons whether quantum mechanics is true, even in a system where there are billions and billions of electrons around that can make the picture more complicated. So yeah, I think, and indeed indeed you have a lot of technological effort, but in the end you get sort of a textbook result. Maybe move forward in your career path a little bit after your PhD, which we talked that it was a science paper, but you had more results from this, but then you moved to Würzburg, and maybe I talked at some point with Anton Akhmerov, and he told me that he feels that people who do very clean experiments in their PhDs get an appetite for doing more adventurous physics afterwards. And that people who do kind of adventurous material physics in their PhD get an appetite for doing the very clean kind of optics-like experiments. And in your case, a little bit that's true, right? Because you got a Humboldt Fellowship to move to Würzburg as a postdoc. And the research you did there was, let's say, in materials that are less clean than gallium arsenide. Yes, I think that's been true for everything that has followed my PhD. The idea was to take materials that were a bit more novel, a bit less mature, and try to get new insights into this material by using the tools that were used on gallium arsenide and developed for gallium arsenide, which is such a high quality platform and very well understood. And yes, that's more adventurous. That's also a way for me to push the boundaries, in the sense that, of course, many of the novel materials come from groups which have an expertise in growth, or and usually that comes with an expertise in basic transport, but rarely that comes with an expertise in more advanced techniques such as microwave transport or current correlation measurements and so on. While in my case, I have absolutely zero expertise on material, so I try to compensate this by bringing my knowledge on these more advanced techniques in a way to the people who can grow good material. And by that, I want to learn more and show and demonstrate that their material is interesting and viable for further application or not. I want to understand the basic physics in this material based on my knowledge and combining it with their knowledge. And that's been the
theme.
Theme for the, yes.
So in Würzburg, indeed, that's the group of Laurens Molenkamp, which is working on novel materials. Like, it's actually an amazing story. Laurens Molenkamp was working on this mercury telluride even before it was cool, in a sense.
Yes.
Because like they were growing mercury telluride. What were they wanting to do with it originally?
So mercury telluride originally can be grown to fabricate 2D electron gases or quantum wells also, except that it's a strong spin-orbit coupling material. So they wanted at the beginning to marry the physics of basically gallium arsenide like quantum wells with strong spin-orbit coupling. And I've never asked Laurens whether this was true or not, but the legend in Würzburg was that they were at some point considering shutting down the activities because they could never get the material to be fully insulating in the gap. And that, at the beginning, they thought was a sign of the poor quality of the material. They had been working very hard, but could never make it very insulating in a region where it should be insulating. And then came all the hype about topological materials, where it was basically explained that in the gap, there should be residual topological states which make the system non-insulating by nature. And these topological states are very, very interesting for basic physics and potentially open perspectives for applications. And of course, Würzburg was fully ready and fully equipped for that. So they jumped on this very rapidly and published lots of high quality and high impact papers very, very early on. And when I finished my PhD, this seemed like a natural continuation for me, where I could learn a lot about these new materials, learn a lot about their fabrication and the material growth, which, as I said, are not my strong point, and bring my ideas and expertise on transport.
So back then, also it was the Humboldt Fellowship which played a part in bringing you to Germany. That's a early career postdoc grant, which I guess, on the one hand, gives you pays your salary and expenses and so on, but it's also like it's a very important program, right?
Yes. So I'm very grateful for this opportunity. I think my experience with the Alexander von Humboldt Foundation is extremely positive. They provide you with a grant which covers your salary and gives you a comfortable situation for 2 years to make a postdoc, but there's also everything that goes around it. They really make sure that you are comfortably installed in your new location. They send you a dictionary if you want to learn German. They send you a few goodies. They organize meetings and networking events where you meet the other grantees. I think it's a very, very attractive opportunity for the people who want to come to Germany as postdoc. I think they should really consider applying. This is a very comfortable situation. This looks good on your CV as well, if you're interested in making a career in academia afterwards. I really enjoyed it.
And I think indeed the German research landscape benefits from bringing in people with new expertise that have a sort of, that also come in with the confidence boost and the relaxation that this fellowship brings, and then can do good research. So indeed you immediately worked on sort of the interface of superconductivity with the topological insulator 2D materials, right? And
I did a little bit of, I did a few things outside of that, but this was not super successful. Yes, I did mostly I did mostly work on the interface between superconductors and topological insulators.
Well, I guess because in a weird way, the electron quantum optics you did during your PhD is one way to marry optics and electronics. And the research with Josephson junctions on maybe strange materials, but also more in general, is another way to essentially marry optics and electronics in a way. Was that something that you were immediately aware of, or was it something that you discovered along the way that was kind of nice and convenient?
I think I mostly discovered along the way. I was aware that there was a big activity related to quantum circuits based on superconducting materials, where people were looking at the quantum properties of circuits based on this material, because they have extremely low dissipation, and that sort of helps. And because the Josephson junctions themselves are extremely extraordinary components. But I discovered the richness of that field as I started to work. And there I must say that I was lucky enough to work with two big names in the field. Laurens Molenkamp on one side, who has a very well-recognized expertise in transport in general, in materials. So he has expertise in both growth and transport. And on the other hand, with Teun Klapwijk, who is probably one of the most famous physicists for his research on superconductors, ranging from basic aspects of bulk superconductors to more advanced circuit-oriented superconducting devices. And I really enjoyed that time very much. I really learned a lot. And that was extremely good to marry both aspects, both material aspects with the device and Josephson junction aspects.
Yeah. So yeah, exactly. So the postdoc was a really good, on the one hand, a place where you could learn and do, like, open up new science, but yeah, also quite productive. And then afterwards you could return to Paris, and that's also again a difference maybe between the French and the German system, because once you return to Paris afterwards, it was it was kind of possible to relatively quickly get a permanent position in the École Normale Supérieure. Right?
Yes, so the CNRS and more generally, I think the French system tries to favor hiring permanent people at a very early age. That fluctuates a little bit depending on the amount of positions that are open, and this is related to economy and other factors outside of research. But the main idea is that they try to hire people young and to give them conditions where they can do research for the next 30 years without wondering whether they can continue in academia, like to free them of all the problems that you can feel when you're in a non-permanent, in a temporary position. And I think this is something that I enjoyed, going back as a permanent researcher and then forgetting about the stress of finding a new postdoc position and things like that. And Yes, that's one of the major differences with Germany.
Yeah, and in the big, like, as a permanent researcher in France, do you have teaching duties, or do you really can you go to the lab and work in the lab?
So again, the French system is a little bit special in a way that it marries two different types of permanent positions in research. There are positions given by universities, and these positions come with a teaching duty, which is actually quite high, and that can be difficult for the people who have such position. And on the other hand, the CNRS, which is a national institution for scientific research, the CNRS has position without any teaching, just purely research, that they give to labs with which they are associated. So often the labs are associate the CNRS together with the university. That's called a mixed research unit. And in these mixed research units, you have both university personnel and CNRS personnel.
Yeah, I guess that probably also generates some friction between the.
Yes, that can generate some friction. Now there's a way to mitigate that. Because the CNRS personnel has less teaching duty, it's expected that they also take a little bit more administrative duties.
I see. No, okay, that makes a lot of sense. Then indeed, let's quickly just fast forward to the future. After this staying in Paris for a while, you now joined University of Cologne last year. After 2 years ago, no. As a W2 professor on tenure track to W3. So, of course, one of the things is your professorship is directly linked to ML4Q. It's also cool. Which is the ML4Q&A podcast here. So we have to briefly mention that. In a way, you again have a similar situation to the Würzburg move, right? You have, on the one hand, new materials to explore here.
Yes, so I have a new material which is provided by the group of Yoichi Ando here in Cologne. So that's really good to have this collaboration on very short distances because Yoichi is basically, I think, less than 20 meters away from my office. So we can have this very close collaboration. We again marry our respective expertise. So that's also very exciting. We participate in the larger scale activities of ML4Q, which combine, as you probably know, matter, light, information, communication aspects of quantum computing. So that's very exciting, yes.
I did on purpose, like we didn't talk much about quantum computing on this episode, but I think that's fair because indeed a lot of these electronic properties of novel materials is, to be honest, quite far away from building computers. We should mention during your time in Paris between Würzburg and Cologne, you also took part in a high-profile experiment on anyons, which is topological particles, which is quite similar to your PhD research in a way, right?
Yes, so this experiment was a natural continuation for what had been done by myself and by my successors on this electron quantum optics. So the idea is now to move away from the electron systems to go towards anyons, and anyons are one type of particles which have quantum statistics which is neither bosons like photons or fermions like electrons. And these anyons, the name comes from any. They can have any statistics in between electrons and bosons, or fermions and bosons. But they only exist in a very limited, in only a very small number of systems. And one of them is two-dimensional electron gases in gallium arsenide pushed towards the so-called fractional quantum Hall regime by a very strong perpendicular magnetic field. And these anions are known to exist in a way for a long time, or predicted to exist. And one of the things that had been seen already very early on is the fact that these emergent particles have a fractional charge, and that has been seen already. But one of the things that was missing and that was crucial is the fact that they also have a weird statistics, which is not the ones of electrons and or photons. And there I have mentioned already that our measurements of current fluctuations is a way to have to see the footprints of these quantum statistics. Well, my colleague Gwendal Fev pushed this idea a little bit further to try to see the footprints of anionic statistics in the correlations, in the fluctuations of the current in this system.
Yeah, exactly. And in a way, it's really a beautiful thing at the bridge between where you are now and where you're going, because some of the topological materials that we are looking into in Cologne in principle can also show anions. And it's also a nice historical touch because, I mean, the original idea for anions and for topological phases in matter came out of research on gallium arsenide originally. Like a lot of the historical.
Yes, these are very strongly connected histories.
Yeah.
That's for sure.
So in that sense, it's quite exciting. And I'm a postdoc with Yoichi, so I'm very excited to continue working on this. And for me, it's also a privilege to learn some of your experimental techniques because they're very different from what we currently do. So it's very exciting to have you here, and I immensely enjoyed this podcast.
That goes both ways. I enjoy it very much, and I also learn a lot from all of the expertise around, including yours.
Thanks. Then I think we can stop here, and thanks a lot for being a guest on the podcast.
Thanks a lot for having me.